This is the fourth time I'm in Edinburgh in this place, so I quite like it. Okay, so we start with one equation. Surface over the rails. If you make a drawing, find that real points are here, here in infinity. It's just one real connected component. And if you're clever, you write x squared plus y squared divided by x squared plus 1 equals u. And then you make a change of variable. X plus iy equals x plus iy divided by u plus I, where I squared is minus 1. And you find that this is birational to x squared plus y squared equals u. And of course, this is a rational surface over the ground field. It's parameterized by x and y. This surface x is birational over R P2R. Now, the general theorem, which we already heard in the talk of quadric manga, is that if you take, which is due to Kamesati, in the paper, which I think these days nobody ever read, but anyway, 1913, and I still, in fact, as in his book, as a proof that if you take x over R, smooth projective, so I won't always say that, but smooth projective, algebraically connected variety surface in that case, if xc is birational P2C, and x of R connected and not empty, then this implies that x is birational to P2R. Let's look at whether the connected components of the real locus is just one, then the variety is rational. So for conic bundles, it's rather easy to prove. In general, the proof goes through the classification. So there's a question is whether kind of thing that generalizes. And so the main question here will be, we look at X or P1R, a family. So when I write this, I always think that X is smooth and projective. X over P1R is dominant. A family of quadric surfaces. So this is X is dimension 3 here. X is 3. And we ask, so question, if X of R not empty and connected, does that imply that X is birational over R P3R? So, and a case which is of your interest, at least to me for quite a while now, is this equation. It looks like the one here, except that I put 3 squares on the left-hand side rather than 2. And now, if you want to stop listening, you can spend the rest of the half hour or less than a half hour thinking, is this birational to P2R? I do not know. And initially, when I started this type of lectures, I dared not reveal this equation because I thought somebody in the audience after 5 minutes will tell me this is birational, but this has not happened yet. So it happened this time. Yeah. So we'll come back to the equation. But for the timing, I want to look at quadric bundles. And so first of all,
P2 is a no, right? The answer is no.
Right?
Yeah.
It's real. Thank you. Thank you. Good stuff. So, some general words about rationality. Okay, the field X over K is an smooth projective. And now we have implications. X is K, so K rational. When I say K rational, means birational to, so by definition, X is birational to PDK, where is the dimension. So we have an application that X is k-rational implies X is stably k-rational. Implies, well, that implies that X is equal to so zero trivial. So we did this. So you have to know what is the Char group of a variety. So if you have a variety X over K, the Char group at 0 cycles is the free group divided by the divisors of functions and curves. Curves. So the drawing is this. You have your variety X. Each time you see a curve, C, and the rational function in curve C star, you take the divisor of the function of the curve, and that creates the zero cycle on the curve, and therefore on the variety. And you decide this is going to be zero. Okay. And then this, if X is proper, as projective as it is here, there's a degree map. Is 0 of X to Z, which sends a close point to the degree of the close point of a K, and the kernel is A0 of X. So that's an and so you said here is zero trivial, that I always assume that X has a rational point. And I consider this means that A0 of X F is equal to 0 for all F containing any field F containing K. I go over to F and I look at the Char group 0 cycle. I want this to be 0. And this is also equivalent to the fact that if you look at simply X over the function field of X itself, this is 0. And in the fancy language, in the language of the other guys, this is called decomposition of the diagonal. So, and this thing here, this one here, this implies that lots of partial invariants are trivial. This is enough to imply this, or zero, or trivial. For instance, bar group of XF divided by bar of F is 0. And also, the map from H3F coefficients in anything, I mean, mu n and for I, H3, and this is a group that will come up in the lecture. F of X over F, mu n, mu n times 2 would be the one that would come up, but never mind. So yeah, if you look at the Galois homology of the function field of X, there's a way to define each time you have a discrete variation on the function field which contains the ground field. You have a way of defining a residue, which takes place in this case in H2 of the function field of the residue field of at this point of connection 1, and you look at the classes which have trivial residue everywhere. Okay, that's a generalization in a higher dimension of the Brau group, and so if you have this property that X is trivial, then your defined homology will be trivial. The background. Okay, now answer to the question. So the general question, so this is one example. But the general question, the answer is no. Okay, and there will be several no. So no one. No one, I write down equations. X squared plus, so I'm sorry, I did something wrong. All this is joint work with Aniana Periodica, which we did in New York in April and May. Okay, so number one, in fact, we found that the last day I was, the last day I was there, u square y square minus u z square plus t square equals 0. This is in A1u plus P3. So this parameter here, then you have it's homogeneous in X, Y, Z, and T. And so this and you write down this, if you look at it, you'll find that it looks something like this. You have 0, you have infinity, then and special fibers there look like this with a conjugation. They're over R, but there's a conjugation. In fact, one has to blow up if you something here if you want to get a smooth projective hole, but never mind for the lecture. And the real points are here. X of R is connected. But Brown group of X divided by Brown of R is not zero. And therefore, X is not rational. It's not even stably rational. And when checks that the class -1 U, which belongs in the Brown group of R of U, if you push it into the Brown group of R of X, it gives something unramified with respect to R and non-zero. So this class downstairs in the Brown group of the real line, which is ramified, so certainly it's not zero. In fact, it doesn't die when you go up there and you check it's unramified. So X conclusion, X is not stable rational. Now, when you look at this, you might object, okay, we've taken a quadric surface bundle with very nasty fibers. If the gel take a family of quadric surface bundles, it will degenerate in gel, but it will degenerate into a quadratic cone over a smooth conic. It won't break up into pieces like this. So you can ask, let's look at nice quadric bundles where all the geometric fibers are irreducible.
Total space is singular.
Right?
Total space is singular.
This one is singular, but in fact, you have to blow up. And in fact, the paper of Alexei, one of the first papers by Alexei, where you get some singular points and then you have to blow up and you can write it down. But because if I use unramified cohomology, I don't have to think because I just compute with discrete variation. So from now on, we're going to look at nice vibrations. And vibrations will in this talk will always mean family of unless I say something else, a family of quadric surfaces over P1. So we look at nice vibrations. That is, I assume that all the bad fibers are quadric cones. Over C, this is all. It's the only way in which it can degenerate. Okay, so now, so now the no two is that in the paper of Hassett and Schinkel, on one of their many papers, one about intersection of two quadrics in P5 over R. In the little corner, you will find that there exists such an X of R non-empty, X of R connected, and X is not birational over to P3R. So X22 means smooth intersection of two quadrics in P5. Okay. And this uses what is now called the intermediate Jacobian-Tolson method. Okay. And it doesn't say about stable rationality, but it says it's not rational. And now if you have an intersection of two quadrics like this, what you do is you take a point and you project from that point and you transform it into a quadric bundle. So you can, this X actually, you fix a point, you project from the point, and you transform that into an X dash to P1R. And because the X22 was smooth, what happens is that this vibration is, in fact, a good vibration of that type. And so now we have an example of such a good vibration, nice vibration, with X of R connected. Nevertheless, X is not birational to P3R. So a few more words about some general words about vibrations into quadric surfaces. If you have a vibration into quadric surfaces, there's associated to it a ramification covering the curve delta. So if the joint fiber x theta is x squared minus a of t y squared, sorry, a of u y squared, minus b of u y squared plus a of u b of u d of u t squared, so 0. The covering here is given by w squared equals d of u. And if you, so that comes with it, and if you go over to this, the d of u becomes a square, and you recognize a quaternion form. And then on this w, there's a nice class called alpha in bra group a priori of the function field of delta. The class of a of u, b of u, which downside than P1, it's a bit strange because this is the of u, but if you go over to delta, that class here is well defined, and not only is well defined, but it lives in the bra group of delta. So that's because it's a nice vibration. So it's unramified and delta. This class here. And so let me denote by star the condition alpha is not in the image of bra of k plus the bra of delta. Getting tough. Okay, so let me very briefly, Wittenberg has many examples of x to P1, P1R, which are nice. And alpha is not, so alpha is alpha not in the image of product K plus the product delta. But x is not directional to P3R using the IGT method. Now, what we started with Elena was to try to understand this A0 of x for quadratic bundles over P1. Okay. And because time is very so short, I will. So, okay, so suppose x is to P1. Okay, is a nice vibration. Then back in 1997, Skorobukatov and I we investigated the group A0 of x over K. We're interested, in fact, in what happened over a number field. But now, today, we're going to look at what happens when, instead of taking the number field, we take the function field of x. Okay. So we proved that I decided to skip. No, we didn't. I didn't skip. So there's an injection from A0 of x into H3 unramified of the function field of delta. This covering, okay, coefficients n mod 2, divided by the image of what? Of H1 k coefficients n mod 2, cap the class of alpha. So this alpha, because we're alpha, I can also view it as a class in H2 of R of delta, unramified, in fact, it's n mod 2. So this alpha, which is defined. So there's an injection, and this is quite explicit. So again, we look at the cohomology class of the Galois cohomology of the function field of delta with coefficient n mod 2, which are unramified, module this. So we produce this injection. So this gives a control on A0 of x. Yeah, this complicated looking group. So now, because the time is short, so I'm going to concentrate on the case y squared plus z squared equals u p of u, where this is over R, and p of u is positive on Okay, and then in that case, what happens is that these type of equations have the property that the alpha, in fact, is just -1, -1. So precisely, it is the case which is not. It doesn't say, well, this condition is not fulfilled, and the IJT method doesn't work. Okay, so we're in a very special case, but in the special case, the intermediate Jacobian also doesn't work because this condition is not fulfilled there. Okay, so this is a equation we look at. And so, what is the outcome of applying this theorem here? Jump to the right. So so we have the Rx, which is this affine model x squared plus y squared equals u, P of u, where P is positive. We have delta, which we've already seen, which I'm going to write as w squared equals v P of minus v. For some reason, I changed the variables. Okay, and then we introduce. So this is a hyperelliptic curve. So if P is of degree 2, which is already a case of interest, you get an elliptic curve here. And we introduce the product or original geometric rational surface of a threefold by this curve delta. So equivalent properties. So theorem. One A0 of xf is equal to 0 for f containing k. So x is phase 0 trivial. 2, well, I already said that it's enough to show it for the function field for x, the function field of x. 3, the symbol u plus v -1 -1 in H3 of R of W, coefficient n mod 2, is 0. Okay. Here, u and v are functions. U is a function, an inevitable function on some open set of x, and v is an inevitable function on some open set of delta. So I can look at u and v. These are functions which I pull back to x, and I can add them. I add u and v, u plus v. That's a rational function in W. Here I have -1 and -1, and here we're taking coproducts by using H1 z mod 2 cross H1 z mod 2 into H3. And now, if you don't like Galois homology, there's a very simple translation, which is u. In fact, the translation is not trivial. Which is that u plus v is a sum of 4 squares in R of W. Okay, so we have u, which is a function on x, v, which is a function delta. We pull them to W, we add the two functions, and we want them to be a sum of 4 squares. So that condition here is equivalent to the fact that x is, say, 0 trivial. And then there's a fifth condition, which is that I call f the function field of delta, the map from H3 f z mod 2 to H3 ramified f of delta or f z mod 2 is an isomorphism. Good. So now,
sorry, just to make sure, all of these are u plus v.
U is a function in delta. Sorry, u is a function on x. V is a function on delta. I pull them back to W. I get two functions on W, and I add them.
But your function delta was defined by W squared equals VP minus K, right?
V to W squared, yeah.
Right. Yeah. So Yeah, but V, you're still using V, which is still a function of P1.
V is a function on delta.
No, that's right. No, that's right.
So. At least I have one.
I mean, sorry, you have to replace V by U. I mean, that's what Mignon said.
Oh, here.
In the equation of-
No, I wanted to put a V here. I didn't want to put this U.
No, that's right.
Because the initial equation was W square equals minus, if you look at the equation, there's a minus that comes up. It's very important. Minus in this game is very important. If you look, because it's x squared plus y squared equal U P of U. Minus U P of U. So when you do the computation, you would get minus U P of U. And so I decided minus U will be V. Many mistakes of that kind when, but I'm pretty sure of that. No, thank you. Cool. I have time for one proof. One proof is that we take maybe I know I won't give the proof. I won't give the proof, but the proof is simple. So if we look at x squared plus y squared, z squared equals U P of U. And P of U is, so I consider to the case where we get the clever genus one, that is P is of degree 2. So U squared. Then the theorem is that if B is positive, so B actually has to be 0, and also A squared minus 4B is negative. So if B is at least A squared over 3, so here we have B at least is bigger than A squared over 4. Yeah. So that comes with the hypothesis that this thing is positive. But if B is at least A squared over 3, then in fact, we can show that U plus B is the sum of 4 squares in R of W. By complete explicit computation, it takes a few, just 3 lines, but I won't write them. Yeah. So one remark I should have made, and I have still, I want to make it, is that if you look at these equations up there, you find that P of U is a positive function on R. So it's the sum of 2 squares. So you see that in this function field, you have a sum of 3 squares, which is U times the sum of 2 squares. So because sums of 4 squares by sum of 4 squares, but by sum of 4 squares are sum of 4 squares, as Euler told us, we find that U is a sum of 4 squares in the function field here. Similarly, P of minus V is a sum of 2 squares. So V is a sum of 2 squares. So U plus V a priori is a sum of 6 squares. So U plus V, from the equations, you find that U plus V is a sum of 6 squares. But the question is whether it's a sum of 4 squares. Okay, so there are it is basically 1 minute left. So how shall I get out this problem? So we have a theorem 1 here, and we have a theorem 2. Which is, we look at x squared plus y squared plus z squared equals U P of U, degree 2. So as before, U squared plus AU plus B. And we consider the curve E, the elliptic curve given by z squared equals U P of U. And so now we look at, so suppose the envelope is over C of the curve EC. So suppose that E has complex multiplication. E has complex multiplication. And moreover, that this thing is isomorphic to Z omega, where omega satisfies an equation of omega squared plus C omega plus D equals 0. This is in Z, this is in Z. And C is odd. And in that case, we managed to prove that A0 of X F is 0 or F containing. Okay, I have no time to explain the proof, which is longer than the proof at theorem 1. So the outcome is, so we're discussing the case u square plus au plus b for the right hand side with this condition that this polynomial is positive. So so we in theorem 1 we have a condition about a square over b, and in the theorem 1 we don't have such a condition, but we have this condition about complex multiplication of a certain type. So you can ask when we look at the curves E equals u square equals p of u equals y square is z square equals u p of u. Instead of looking at these A and B, which are not do not speak too much to mind, you could think of the J invariant of E. So what happens is that with our conditions, the J invariant of E varies between minus infinity, 0, and 178. And so theorem 1 covers all ellipticals of that type, which are here. And theorem 2 covers, well, curves with complex multiplication, but the J invariant takes only account Leibniz values for such a thing. And so you could ask, what can you say about them? Well, Zarin showed us that in fact the odd J invariants are dense in the whole thing for the usual topology. So we have other points where we know the A0 of xf is 0. Here we know the A0 of xf is 0. But well, I mean, the other ones, it's an open question. Okay. So maybe I stop here.